Welcome back to Fat Mama Physics. In this video, we are going to talk about the two types of collisions: elastic collisions and inelastic collisions. What I really want to do in this problem is to show how a question may ask you whether or not a collision was elastic and inelastic and how you can go about solving that. But before we do that, I'm going to do a quick little brief tidbit on what the information that you need to know. So what is an elastic collision? An elastic collision is when the total kinetic energy inside your system is the same, is constant. Meaning before the collision and after the collision, you will still have the same amount of kinetic energy. And since in this case we are talking about an isolated system, you have a case where there's no net external force acting on your system, your total momentum will also stay constant, okay? But then what about an inelastic collision? An inelastic collision also happens, and assuming that there are no net external forces acting on your system so that your momentum, total momentum, stays constant. But in this case, some of that kinetic energy you started with gets converted to other forms of energy. So after the collision, your total energy is now different. So here, this is not constant. Examples of inelastic collisions are, for example, let's say I have a car crash. If like a car comes in, crashes into something else, they get stuck together, or if they rebound off, one may go one direction, one may go another direction, or if they stick together, they just go forward, stuck together in a ball moving forward. Okay, so if that were the case, in a crash, you might have all that motion energy, kinetic energy, being converted into, say, sound energy, thermal energy, and heating up the two objects. It may be used to deform the cars and the objects itself. So that kinetic energy gets converted. So as a result, total kinetic energy does not stay the same before and after the collision. In fact, if two objects stick together completely, this is called an completely inelastic collision, in which the system loses the max amount of kinetic energy possible. And this is evident in, say, like we talked about, when objects collide and they stick together. You might be thinking, oh, well, I can visualize what an inelastic collision looks like, but what does an elastic collision look like? I have the example right here with here there are two bowling balls, and they're hung by string attached to the ceiling. So let's take a look.
Back and let go, it stops, and the other one goes out with about the same speed.
You might be thinking, oh, that's kind of like Newton's cradle. So here, I'm going to fast forward here.
This one, not as much.
Okay, starting at two different heights, and look at after the release.
So they meet roughly in the middle.
Oh, notice, isn't that beautiful how they just exchange the relative heights? So the only way for that to happen is if the first ball imparted the same momentum on this ball, so that it leaves the bottom with a certain velocity, allowing it to go to the same height the first ball achieved, and the second ball imparting its momentum on the other ball, the first ball, and it achieving a slightly lower height because they kind of exchanged velocities in a way. They exchange momentum. Exchange momenta. So in that particular case, the kinetic energy before the collision and after the collision stayed the same. That's cool, right? We like elastic collisions. They look very nice, just like Newton's cradle, and almost like Newton's cradle. Not all Newton cradles are perfect. Okay, so you might also, so now you have a sense of elastic and inelastic collisions, but then you might be wondering, what's the difference between momentum and kinetic energy? They just feel like the same to me. One thing about kinetic energy is that because it's a form of energy, it can get converted to other forms of energy, like potential, like thermal, etc. But then momentum, because we're talking about motion, is mass times velocity. It is a vector, so we talk about which direction the momentum is in. We don't do the same thing with kinetic energy. But the thing with momentum is the fact that you can transfer that momentum somewhere, so your object will then lose all the momentum, but when it does transfer to somewhere, it transfers in the form of applying some force on something else. For example, if I throw a sludge against the wall, it transfers all that momentum to the wall, and as a result, it applies a force against the wall, and it loses all that momentum as a result. Okay, so that's kind of the idea of momentum. The momentum is able to perform some sort of force acting on something else, and energy is able to do work or gets converted to other forms of energy. And you might even see in your data booklet that there is an equation that relates kinetic energy and momentum, and it kind of looks like this. You might be thinking, oh, how do I get that? I'm going to do a quick demonstration how we get that. First, we need to know that momentum is mass times velocity, and we need to know that kinetic energy is 1/2 mv squared. And you're thinking, oh, hey, there's mv in there. That looks like momentum. But hey, don't forget the velocity is squared. But we can remedy that to make sure there is enough mass to go around by multiplying both sides of my equation by mass. If I do the same thing to both sides of the equation, it's equally fair. So then as a result, I'm going to get mass times kinetic energy is equal to 1/2 mass times velocity. And I'm going to separate, and remember, if I multiply, it doesn't matter which order I multiply in, so I might as well separate these. I have mv, and then I have another v, so it kind of looks like that. So I'm going to put mv, and then since I'm multiplying by another m, I get m again, and that other v I'm going to put right beside my m, just like that. And because mv is p, is momentum, I can just write this as p instead. What's p times p? I get p squared. It's just like my son pooping more poop. Anyway, so then I can just divide both sides by the mass, and then I'm just going to get kinetic energy is equal to 1/2 or p squared divided by 2m all on the bottom, just like what you see in your data booklet. Okay, so that's how your momentum can be related to your kinetic energy using all the symbols we talked about. Okay, enough about all that talk. Let's do some examples. So I actually pulled up the previous example here, but this time I'm going to ask you, was the collision elastic or was it inelastic? Show our work below, okay? I do example, well, technically this is example 1 continued, example 2 continued. So I do example 1, you do example 2. Okay, let's get started. So in order to figure out whether or not we have an elastic or an inelastic collision is to figure out whether or not the total energy before and after the collision was the same or not. So I'm actually going to do a table here where before the collision and after the collision. And what I'm going to do is I'm going to calculate all of my kinetic energy, the kinetic energy of all my objects before the collision and all of the kinetic energies of my objects after the collision. Okay, so if we go back to the first example, I just want to write down the final velocity of our second mass, our 8 ball. And that was 1.5, not rounded, so that's V2 is 1.5 meters per second. So let's write down all of our knowns right now. Okay, so we know the two masses is 0.25 kilograms, and just judging from the velocities before, 4.5 and 5.0 meters per second versus the final as 1.5 and 2 meters per second, I can already tell you it's inelastic because the total kinetic energy definitely changed. We definitely have less after the collision, but let's just calculate it, all of it through, just so you have an idea. And notice I don't care about the directions anymore because we're talking about energy, which is a scalar. So let's remember our kinetic energy is 1/2 mv squared. I'm just going to go ahead and calculate all the kinetic energies of the masses. And I didn't put in units just so we have enough space here. We get 2.53 for the first mass and 3.1 for the second mass. And I'm not going to really care about sig figs right now because I'm pretty sure that's going to give us a bigger number compared to after the collision. Unless the question specifically asks you for the total kinetic energy, I would probably have to do some proper adding and rounding after that. So then after the collision, we're going to do the same thing for mass 1 and mass 2. I get 0.5 joules for the first mass after the collision. And I get 0.28 joules for the second collision. Okay, so then I could do a quick addition here just to do this properly. So that's going to give us 5.63 joules versus here, this is a total of 0.78 joules. Okay, so definitely we have a greater initial kinetic energy to start with in our system than our final. Therefore, we know that this must be an inelastic collision. Okay, so that is how we show our work to prove whether or not your system your collision is elastic or inelastic. In fact, this collision here would just be a normal inelastic collision if the two balls were stuck together and they move together, which really doesn't happen in a pool game. But if that were the case, then we would call that a completely inelastic collision. Okay, so hopefully that gave you some insight on how you could do these kind of problems. Okay, and if you don't remember the final velocity of our system after the two cars ram into each other, we know that the final velocity was 18 meters per second, according to our previous video. So good time to pause the video. Now I'm going to do the solutions on fast play. So we're going to divide this into the before and after kinetic energies. To calculate the kinetic energies before, first we have the mass of the cars is 1,500 kilograms. We have its initial velocity as 50 kilometers per hour. To convert to meters per second, we got to divide that by 3.6. And then for the truck, it is 4,500 kilograms and it has 70 kilometers per hour of speed divided by 3.6 gives us its meters per seconds. I'm going to go ahead and put all of that into my equation. So that's 1/2 mv squared for the car, and putting the 50 divided by 3.6 in brackets and squaring it gives me the kinetic energy. Doing the same thing for the truck, but for 70 kilometers an hour, and taking all that squared gives me that number. Now we're going to calculate the kinetic energy after the collision, and both of them have the same velocity since they are traveling together. They're stuck together at 18 meters per second. I put these values into our kinetic energy equation for the car and the truck. We add these values together. We notice that the kinetic energy before the collision is greater, so there's a loss in kinetic energy overall, meaning that this is an inelastic collision. And since they are stuck together, this is in fact completely inelastic collision. Okay, so here are the solutions for example 2 continued. We show that the kinetic energy before is greater, not by a lot, compared to the kinetic energy after the collision. Though therefore it is an inelastic collision, and since these the car and the truck were stuck together, we have a completely inelastic collision as a result. And in here, I just want to mention why I put divided by 3.6. That's just to convert the kilometers per hour to meters per seconds. So that's why I have that there, okay? So hopefully you learned a little bit something from this video that you can apply into your own practice. Good luck with that. Thank you for watching, and Fat Mama Physics signing out.